If I told you that 10 was really 16, would you believe me? Because you should. By the time we're done here, we will examine the process of moving from binary to decimal to hexadecimal so that we can become comfortable with the IPv6 address format. I know, this is one of the biggest hurdles to get over, is you're used to IPv4, you're used to working with binary and subnetting and things like that, and now it's like, here's this giant address, and it uses letters, and how does that all work? This is step one of that. We're used to looking at things in terms of base 10. Now, we never call it that because we're human beings, and human beings say things like decimal, because decimal works like we're used to it working. 0, 1, 2, all the way down to 9. You reach the maximum for that place, base 10. You then go to 0, carry the 1 over, all the way down to 9, right? Go back to 0, carry the 1, you're now at 20, and so on and so forth. That's how we're used to counting. And when we first learned IPv4 subnetting, we learned about something called base 2. Now again, being human beings, we don't call it base 2, we call it binary conversion. The reason that it's base 2 numbering is because there's literally only two values, a 0 and a 1 that it could be. So when we're using numbering systems like that, we have to have rules that define what it means. Like when we're converting from decimal to binary, we say, okay, the rule is we use powers of 2. So if I took the number 52 and said, make that a binary number, we would go, okay, well, the powers of 2 are 128, 64, 32, 16, 8, 4, 2, 1. Our first one, no, yes. So subtract that. We've got 20 left over. So there's our 20, right? So that's the binary equivalent. And we can do that because somebody much smarter than you and I, said, let's make a rule. Let's make a rule that says the powers of 2 will line up to those binary numbers, and that's how you can convert back and forth from binary to decimal. Well, base 16 is what we use for the IPv6 world because our addresses look like this. And when you start seeing addresses with letters in them, you should start being flagged that, hey, this is now a base 16 numbering. And we don't call it that. We call it hexadecimal. Because in the hexadecimal world, you count from 0 to 9, 1, 2, 3, just like decimal, and then you hit 9, and instead of zeroing out and going over to 1, you just continue on. A, B, C, D, E, F, right? 16 total values, and when I add 1 to F, we go from 0, carry the 1, and we're here at 10. And now we're back to the introduction where I said, if I told you that 10 was really 16, would you believe me? Because you should. Well, you kind of should, but you wouldn't, because 10 is how we call the decimal number. We would never call a 10 in hexadecimal 10 because that would be very misleading, right? We just say, okay, it's a 1 0 in hex, right? Which would tell us that's really the 16th value if we start counting from 0. So let's take this a step further, because at the end of the day, it's just numbering schemes. It's not weird. It's just different, right? So when we're looking at binary values, which is how the computer works, we have to know, how does the computer see these things? That's what really helps us process, especially as we get into the subnet mask and bits and all that kind of stuff. Well, the computer only has one way of processing, and that's with ones and zeros. That's why we call this 128 what? Bit address, because essentially we can convert this into 128 ones and zeros. But how do you do it? Well, think of it logically first. It's a 128-bit address, and there's 1, 2, 3, 4, 5, 6, 7, 8 hextets. At least that's the proposed Wikipedia name of these things, instead of calling them octets. By the way, why do they call these octets? Because octet is 8, and there's 8 binary digits that go in each one of these. And so someone just said, let's call it a hextet, and I like that. So there's 8 hextets. So if we divide 128 by 8, that would mean equals each one of these actually contain 16 bits. Okay, interesting. So let's take it a step further. There's 4 characters in each one of these. And when I say characters, I'm doing it in quotes because it's a hex character, right? So there's 4 characters. So if I were to say, let's divide that again by 4, then that would mean each character would have 4 bits that make it up. And that would be 100% accurate to say that. And by the way, that's why we say that the hex characters only go up to 16. Because if you have 4 bits, look at our binary chart, 1, 2, 3, 4, 4 bits, and we add all those up. So 8 plus 4 is what? 12, right? Plus 4 is or plus 2, 12, it'd be 14, plus 1 is 15, right? If we add all those up, it's 15. But you also remember, we also count from 0, right? If all those are 0, that, so really, there's 16 total values that we can get with our 4 binary digits. Maybe it would be a little bit easier if I just showed you this. It represents a table that shows the decimal value, the hexadecimal value, and the binary equivalent. And as we're going down this list, it all makes sense, right? We're used to this, 0, 0, yeah, 0, right? 1, 1, 0, 0, 0, 1, right? 2, 2, yep, that's the 2, yeah, it's 2 to the power of 1, essentially, right there, right? We're used to all of this, until we get to about here. That's where we go, okay, 9, well, in binary, it's that. 10 in decimal is A in hexadecimal. Now, again, a 10 is a 10. If I say, well, hex A, and I put it in some kind of converter, just you remember, hey, actually, hang on, this would be cool. I just had the idea. Let's open the Windows calculator and just go over to programmer mode, because that's where you can see all of these different values. So if I were to put 16 in as just about, I was thinking, why am I not seeing? I meant 10 as a value, right? Right there, it says, okay, decimal, it's 10. I typed it in. Binary, 1010, right? Hexadecimal, we're over to an A. Now notice we're starting to get used to working in these kind of 4-bit chunks, right? Right over here, you see this binary value. In the IPv4 world, we're used to working in 8-bit chunks, simply because that's how the IPv4 address was divided. Each one of those was 8 bits of data. That's why we could go to 255. Well, in the IPv6 world, we have to look at our addresses in terms of smaller chunks. So each one of those, let me just 0000 colon, 000. Each one of these, instead of it being 8 bits, is actually 4 bits of data. By the way, that has a name. And it's kind of fun. It's called the nibble. And it's the same way as this has a name. It's called a byte. So you've just learned that, interestingly enough, there's a name somewhere between a byte and what most people thought was the smallest, a bit. Well, in between those is a nibble. Tell me the creativity of that wasn't lost. It's not a byte. It's a nibble. That's funny. Even if I'm the only one smiling. So each one of those is a nibble of information, and that's where we can see all the way down when we get to our F, we have the binary 1111. We've maxed out that character, if you will. Now, somewhere around now, someone's like, okay, I think I get it, right? You're getting this, right? You've got the binary, the bits, the byte, the nibble. You're getting all this. But it's like, okay, but why? I mean, why hex? I mean, why? Well, the reason why for all of this is because we need a friendlier way of working with these addresses than working in binary. I mean, imagine this if we were to break it into a binary number. I mean, let's try it. I mean, here's how you would do it. You would go, okay, let's look digit by digit, 2. So it'd be 0, 0, 1, 0, right? There's our nibble that represents the 2. A 0, okay, 0, 0, 0, 0. Oh, another 0, okay, 0, 0, 0, 0, right? A 1. You see where I'm going with this? 0, 0, 0, 1. I'm showing you how insane it would be if we had to work with IPv6 addresses in all binary. I mean, imagine like, okay, I'm going to statically assign this address. I'll take a break after it because, I mean, it'd be prone to mistypes. It'd be a nightmare because you'd have this giant thing. And so it would be insane to work with all this in binary. So that's why hexadecimal is here, is because it's a friendlier way. Look, it's a smiley face that we can work with these numbers. Oops. And by the way, I think we just learned how to convert from hex to binary. I mean, did we? Yeah, I think we kind of did. Because now you know that each one of these is 4 bits. And you know that you can evaluate each one independently. Each character should be independently evaluated. I mean, 0, 0, I mean, obviously this is a whole bunch of 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0. So there's a whole bunch of zeros there. But I mean, what about this one? Okay, we got, so that would be 4, 8, 12. So you'd have 12 zeros, right? But you would divide them up into 3 individual groups. And then you have your A. Now, whoa, wait a sec. A, well, that's where you need that chart mentally in your head. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because we're a human being. We like decimals. 11, 12, 13, 14, 15. And then over here, you mentally go, okay, 0 through 9, that's the same. And then A, B, C, D, E, F. If it helps, just put some lines right in between there so you can line them up. So you go, okay, well, A is really 10, right? So when I'm converting this over to a binary number, I'd really look at it as 1, 8, no 4s, 1, 2, no 1s, right? Again, we're back on those powers of 2. 1, 2, 4, 8, because every single one of those characters gives you 4 bits to work with. So if I were a friendly human, I would say, oh, that's 10. If I were a hexadecimal master, I'd say, oh, that's A. If I were a computer, I'd say, I don't care what it is, it's 1010. Are you catching this? It would behoove you to write this table, the one that I constructed right here, that shows the decimal to hex to binary. Construct that on paper. And that, by the way, is your homework. I have 2 homework assignments for this video if you choose to accept it. 1, I want you to be able to regenerate this table from memory. And it shouldn't be hard, because at this point in your life, you know decimal and you know binary, right? You're feeling good about that. You just have to get comfortable filling in that hexadecimal amount. So if you want to kind of rearrange, maybe put the binary over here so you can kind of do those 2 first, and then just kind of line it up and go, okay, well, where 10 takes over, that's where I go from there. That's the first thing I want you to do. The second thing I want you to do is I want you to take this address, which is in hexadecimal, and convert the entire thing to binary. And in so doing, I'm giving you 32 individual easy exercises, right? Because there's actually 32 characters in a IPv6 address, each one of those 32 characters having a nibble worth of information that you would use to generate it. My goal in doing this is not just to fill you with busy work. I'm not just like, yeah, fill a page with binary conversion. It's because I want you to get really comfortable that you can just look at an IPv6 address and be like, okay, got it. So I can flip that over to a binary number and really see how all of the binary behind it is working. We still work in binary. When it all comes down, in the IPv6 world, we're still dealing with binary. It's just not in our face as much as it is in the IPv6 world. You'll see that when we start looking more at the subnet mask. For now, we have examined the process of moving from binary to decimal to hexadecimal to become more comfortable with the IPv6 addressing format. I hope this has been informative for you, and I'd like to thank you for viewing.